Good afternoon, everybody. Welcome to miserable weather-wise Wednesday afternoon. I don't know where you are, but where I am, it's raining, but I just looked out my back window to my backyard, and a lot of my bushes in the tree back there, you can see ice forming on the bushes and trees. So aren't you glad you don't have to get in your car and go to ECC? You're hopefully safe and sound at home. Be careful. It's going to get worse, I'll bet. Unless it warms up. Oop, let me clean off here, whatever. I don't know where that came from. Anyways, let's get started. All right, quick public service announcement from me, the management. Don't forget the hand-in labs that are due. The lab we did last week, aromatic chemicals are due, or compounds are due by tomorrow. It's points you don't want to lose. The lab write-up is not that hard. Hand in labs. All right, today I have my list of to-do list. We'll go through the alcohol problem set, and we'll get back to ketones and aldehydes, which Dr. White loves. So is Mother Nature. Did I tell you Mother Nature is probably one of the greatest of all organic chemists? She is. And we'll do our lab today. So let's get started. And remember, there's no such thing as a dumb question. And tonight from 6 to 7:15 on Zoom, I'll have my office hour. All right, let's take a look at this. On test 2, like test 1, there'll be 3 types of questions. One is general knowledge, another one is nomenclature, and the following is reactions. Speaking about general knowledge, anybody happen to drive by a gas station and think about the fact that in that gasoline, they have 10% ethanol, and that's an alcohol? Did you happen to pick up a bottle of rubbing alcohol and see it has isopropyl alcohol, which is also an alcohol? Remember, organic chemistry is all around you. It won't hurt for you to think about it when you're not in my lecture. All right, one nomenclature question is give the IUPAC name for the following. How do you do it? Let's go to C. You find the longest chain with the hydroxyl group. That's an alcohol. And the longest chain includes the carbon that hydroxyl group is on. You name it as an alkane. This one, 5 carbons, pentane. You drop the E, add OL, pentanol. And when you're not in a ring, acyclic, you need a number of which carbon the hydroxyl group is on. And in this case, you always give, in all cases with alcohols, you give that carbon the highest priority, the lowest number. And it's on carbon 2, so it's 2-pentanol. And oh, it's your old friend, the methyl group on carbon 3. And now if we look at B, we have a ring. You name it as an cycloalkane, cyclohexane. It's an alcohol. It's cyclohexanol. When there are no other substituents, and that's the only thing, you don't need a number. Also, if we look at D, we have a ring, 5 carbons, cyclopentane. On carbon 1 here, I have a hydroxyl group. It's an alcohol. Drop the E, add OL, cyclopentanol. Now in a ring, we don't use the number what carbon the hydroxyl group is on. When it's the only functional group, which is how it will be in this class, it's always number 1. Everybody knows that, so you don't need a number. But we do have an isopropyl group and a methyl. And you number from that hydroxyl group in such a way that the other alkyl groups get the lowest number. Sorry about that, I'm thirsty today. Must be the weather. But anyways, the isopropyl group is on 2, the methyl group is on 3. Now I follow alphabetical order, so it's 3-methyl-2-isopropyl cyclopentanol. But if you had put down 2-isopropyl 3-methylpentanol, you would have gotten it right. Now, let's look at 2. The other type of nomenclature question is draw the condensed structure for the following molecules, organic molecule names. And how do we do that? We start from the right and move left. OL ending, alcohol, if that were D, pentane, 5 carbons, and the hydroxyl group is on carbon 2. Now, I learned this from my professor, and good habits I don't change. I always start from the right counting. So that's why the hydroxyl group is on this carbon. You could have put it on this carbon as number 2. Either one is correct on a test. Now, if we look at C, start from the right, OL ending, then that would be, if it were an E, octane, 8 carbons. The hydroxyl group is on carbon 2. You could have started from the other end, but I start from this end. And then methyl CH3, di means 2, and they're on carbons 3 and 5. Now, phenol is a benzene ring with a hydroxyl group. And just like with toluene, this is considered a substituent, so this is di-substituted ring. And we use orthopara and meta and para. Para means 4, 1, 4. Hydroxyl group is 1, the isopropyl is 4. Now, if we look at F, we start here, OL ending alcohol, if that were an E, cyclopentane, a ring. I'll pick any carbon, most of you are going to put it on the top. And I have my hydroxyl group. Next, I have an isopropyl group on carbon 3 of the ring. The hydroxyl group is always 1. And the isopropyl group is on 3. Now, a while ago, I had students ask, well, could you do the line method too for rings? And I did with the isopropyl. You don't have to do that. Next, the other type of question you'll see on test 2, which you also saw on test 1, are reaction problems. And give the organic product or products to the following. And here, what do we have? Double bond. I'm going to do this real quick because we've already done this in double bond chemistry. Acid, H plus water. Water is HO, HOH. Break the pi bond. One carbon gets the hydrogen, the other gets the hydroxyl group. Follows Markov-Nicholas rule. And that is the carbon with the most hydrogen. So the double bond gets the hydrogen. And the other carbon gets the hydroxyl. This has 2 hydrogens. 1 hydrogen goes here, hydroxyl there. Do you break carbon-carbon single bonds? No. Start with 4, end up with 4. Now, let's look at Zaysev's rule. And Zayssev entered this reaction dehydration. And here you have an alcohol with an adjacent carbon with a hydrogen. Sulfuric acid, H2SO4. Use heat and high heat. Sometimes I don't put the temperature there. And you get a double bond that follows Zaysev's rule. That is, you get the double bond that has the most carbon atoms attached to it. Now, this one, you don't have to worry about it because this is the only carbon adjacent with a hydrogen. Same thing in E. But in F, I have my hydroxyl group. And if I lose a hydrogen from A, I'll get compound A. Because between A and the carbon with the hydroxyl group, you'll form a double bond. If I look at carbon B, which is adjacent to the carbon with the hydroxyl group, that has a hydrogen. If I lose the hydrogen hydroxyl group, I'll form this double bond. How do you use Zayseff's rule? The carbon, the molecule with the most carbon atoms directly bonded to the carbons of the double bond is the molecule you get. Real life, you get 90-10, but I'll make it easier for you. So if we look here, A has 1, 2 carbons. You don't count the CH3. B has 1, 2, 3. 3 is greater than 2, and therefore B is your answer. Next, if you oxidize, and that's what the O in a bracket means, you lose a hydrogen here and 1 from the carbon with the hydroxyl, and you form a carbon-oxygen double bond. You make, in this case, a ketone. And do you break carbon-carbon single bonds? No. Same thing here in H. Now, if you have a primary alcohol, the same thing, but there's a hydrogen here and here, oxidize, that's what the O bracket O means, and you form an aldehyde. Now, important reaction is you take an alcohol and react it with SOCl2, thionyl chloride. You replace the hydroxyl group with a chlorine on the carbon that the hydroxyl group was on. And if we look on K, do you break carbon-carbon single bonds? No. I still have my ring, my methyl groups. This carbon has the hydroxyl, and it now has the halogen. And same thing for L. Now, if we look at M and N and O, the reaction is look for what's different, what's not a carbon-carbon single bond. What am I saying? Oh, yeah, what's not a carbon-carbon single bond or a carbon or hydrogen should get your attention like this. And here we have a hydroxyl group on a carbon, and we're reacting with HCl. HCl is HX. I don't have it written here, but that could be chlorine, bromine, or iodide. And you replace on the carbon with the hydroxyl group, that with the halogen. You don't break carbon-carbon single bonds. So this whole structure is my R group. The carbon with the hydroxyl group gets, in this case, a chlorine. And same thing for N. Here's my 4 carbons. I end up with 4 carbons. This carbon had the alcohol, HX, replace it with bromine. And finally, I gave another example of Zayseff's rule. Same thing, adjacent carbon, hydroxyl group, you form a double bond. You count the number of carbon atoms directly bonded to carbons in the double bond. And A is 2, and B is 3. Don't forget the methyl group. And B is your answer. Any questions? All right. Well, in that case, let's get back to aldehydes and ketones. Now, I had gone through how to do acyclic ketones. We'd already done aldehydes on Monday. Oh, don't forget, if you need help, tonight I have my office hour from 6 to 7:15 on Zoom. Now, let's talk about rings and ketones. Dr. White loves them. So does Mother Nature. We look at this molecule. What's the IUPAC name? What's different? Ooh, oxygen, double bond to carbon. Remember, that's a carbonyl group. I have carbons here and here in the ring that are attached to this carbon. And here, R and R prime are connected in the ring. And what is this? This is a ketone. And how do you name it? You name the cycloalkane the ketone is in, 6-membered ring, cyclohexane. And you drop the E at the end, add ONE, and no number. Because the carbonyl carbon is always number 1, and here there's nothing else, so I'm done. And since this is always going to be 1, always, carbonyls rock. But anyways, they do. If there's something else on the ring, hold on. Junk call, a couple more rings. Sorry about that, but I don't want to turn off my Bluetooth phone to my cell phone. One more. Stop. All right, sorry about that. So here's one for you. What's the IUPAC name for this molecule? Your turn. And I'd like to thank all of you for coming to my lecture today. Thank you. And please be patient. I try and give everybody time to finish. All right, I think everybody's done. Let's do it. What do you see that's different? What's not carbon, hydrogen? Oh, an oxygen, double bond to carbon with carbons here and here. That's a cyclic ketone. Oh, I just remembered something. Don't forget on Monday, I will go through the ether epoxides problem set. Keep up, don't fall behind. Well, anyways, how many carbons in the ring? 1, 2, 3, 4, 5. 5 is pentane. It's a ring, cyclopentane. For a ketone, drop the E at the end of the cyclopentane and add ONE, and you need no number. So that's cyclopentanol. Oh, let's do another one. And here's another. Oh, let me put something else on there. Let's make it interesting. And there you go. Give the IUPAC name for that compound. 3 points each. As always, please be patient. I try and give everybody time to finish. Finish. All right, I think everybody's done. So how do you name this? What's different? What's not carbon hydrogen? This chapter, that's all you have to do. And we have oxygen to this carbon, carbon's here, carbon's here. This is a carbonyl, carbon double bonded to oxygen with carbons attached to it. In a ring, these are connected together. This is a ketone. Name the ring as a cycloalkane, drop the E, add ONE, no number for the carbonyl carbon, because that's always going to be number one. So 6 carbons, 1, 2, 3, 4, 5, 6. It's a ring, cyclohexane. Hold on 1 second. I need more room. And if we're in a classroom, I'd be doing the same thing, because the school doesn't like me writing on the walls, I would assume. But I've dropped the E and I'll add ONE, cyclohexanone. But we have a methyl group and an ethyl. This is 1, 2, 3, 4. So this would be 4 ethyl, 2 methyl. Oh, do I have room? Just snuck it in. This is methyl, methyl. Sorry about that. But that's how you do it. Now, there's 2 types of nomenclature questions. One is, here's the structure, give the IUPAC name. The other is, draw the structure for the following. And how do you do this? You start from the right and move left. ONE ending. Ketone. Carbonyl to 2 carbons. If this were an E, cyclobutane, that looks better. 4-membered ring. And you can pick any carbon and it's double bonded to an oxygen. And that would be cyclobutanone. Now, remember, the carbonyl carbon is always number 1, so you don't need a number, which I want. But let's see if you're up to this one. And what would be the structure of 3-methyl cyclopentanone? Your turn. I got a secret for you. You're doing organic chemistry. Hopefully it's not painful. And remember always, in my class, there's no such thing as a dumb question. So always feel free to ask questions in class here or in my office hour. I think everybody's done, so it's my turn. How do you decode this to know what to draw? You start here and ONE ending, that's a ketone. And if that were an E, cyclopentane is this ring. And one of the carbons will have this carbon double bond to oxygen, carbonyl. This is always carbon 1. Oh, it's your old friend, the methyl group. That's 1. You can go clockwise or counterclockwise. This is the difference. Oh, look, it's my hand. Close your eyes. Oh, look, it's different. No, you just rotated it. Remember, molecules are not pasted in place. And on carbon 3, we have a methyl group. Oh, let's do one more. And why don't you try this? Draw the structure for 3-isopropyl 2-octanol. This is something we did Monday, but let's see if you remember. All right, I think everybody's done. Let's get to work. And how do you decode this to know what to draw? You start from the right and move left. ONE ending. Oh, somebody already wrote it on the board here, so I'll use it. It's a ketone. And here, if that were E, octane is 8 carbons. Here I have 8 carbons, and the carbonyl of the ketone is on carbon number 2. And you can have this pointed up or down, doesn't matter. And then on carbon 3, if this is 1, this is 2, this would be 3, I have an isopropyl group. Now you could have started from this end as 1, but I don't. But either way would be right in my class. And now we know there are 4 bonds to carbon, so I can put in my hydrogens. And here's the molecule. Now, one thing I might have not mentioned, we look at the carbonyl carbon, how come it doesn't have any hydrogens? Well, there are 4 bonds to carbon. Here's 1, 2, 3, 4. And 4 minus 4 is 0. Isn't the math hard in my class? And that's why the carbonyl doesn't have a hydrogen. Now, there are common names for aldehydes and ketones. I'm only going to ask you to learn 2 of them. There's actually a whole common name system for aldehydes, which I know because I've worked with these in both graduate school, academics, and the chemical industry. Now, you should know when it comes to common names, I will never ask you what's the common name of a molecule, but I will ask what's the structure of that molecule. Why do I do it that way? Because when you see something on an ingredients label, you'll be able to figure out what's the structure. Now, formaldehyde is the simplest aldehyde, where R is H. Now, you said, Dr. White, you said R is carbon hydrogen. Well, it turns out there are exceptions to that. And for aldehydes, when R is H, nobody calls it by the IUPAC name, which would be methanal, AOND. They call it formaldehyde. You can write it this way. You can write it this way. And you can even write it this way. They're all the same structure. I like this way because I just think it looks cool. I like showing the carbonyl double bond. Now, acetone is the simplest ketone when R prime and R double prime are methyls. I could have also written it this way. Now, acetone, and this is something you should know, and by the way, don't you love when I'm subtle? Acetone is the simplest ketone. Nobody calls that 2-propanone. This is acetone. Now, one of the uses of acetone is, oops, wrong color. Right color. And this you should also know is nail polish remover. And I should tell you, nail polish is some very, very sophisticated organic chemistry and has been. Even the newer one, which isn't that new. How many of you are familiar with the nail polish you put on your nails? You can see I did my, I didn't do my nails, don't look. Anyways, I don't do my nails, even though my grandfather and my brother-in-law back years ago, going to the barber shop, they had a manicurist, the good ones, and they'd put a clear coat on there. They'd, manicure your nails, cut them, and put a clear coat. I don't do that. But anyways, how many of you are familiar with nail polish to make it dry? We call that cure. You put it under a UV light, a blue light. And that makes a much more durable, stronger coating. That's really what you're putting on your nails. And acetone is really good at taking that off. I'll talk later on about another molecule that also does it, but it's not as good as acetone. So you should know what is the structure of formaldehyde. You should know what's the structure of acetone. And you should know acetone is used as a nail polish remover. I'm going to turn the switch, click off, but I have to talk about something very important, and that is formaldehyde. And I should mention, I worked for, when it was called Borden Chemicals, now called Hexion company, that was the largest, and I think it still is, manufacturer of formaldehyde in the United States, if not the world. And a lot of our products use formaldehyde. My last patent, I used formaldehyde. but formaldehyde is a very dangerous chemical. And one of the uses of formaldehyde is to make a resin. And a resin is a fancy name for glue. And that resin holds sheets of wood together to make plywood, strands of wood to make oriented strand board, and particles of wood to make particle board, which you can buy at any home improvement. Now, in the United States, because of OSHA laws, occupational safety hazard, I forgot the rest of that act. But anyways, that's what it is. For many, many years, I learned about it when I first started working with formaldehyde at this one company. Exposure to a worker in a workplace is limited to 0.1 ppm parts per million. Not that much, or I think it's 1 ppm back then. But anyways, you go outside the United States, they don't have OSHA, especially China. Now, I've got to talk about something sad, but true. That's not what I wanted to do. All right, everybody see on your screen the Wikipedia Hurricane Katrina? Back in August of 2005, wow, it's almost 20 years ago, in another 2 years, but 18 years ago, there was a tremendous hurricane in New Orleans and the surrounding area in New Orleans and I think another state. And this was a devastating hurricane. And it wiped out many, many, many homes, apartment buildings, and people who lived in trailers, wiped them out too. And a sad thing happened. The government, in their haste to find shelter for all these hundreds of thousands of people in that area that was wiped out by Hurricane Katrina, quickly went to trailer companies, mainly in Indiana, and said, we need a lot of trailers made quick. And they made them, a couple 100,000. Well, after a while, people started getting sick living in those trailers. And they were called afterward Katrina trailers after the hurricane, why they were made. And there's a very brave woman, Becky Gillette. And Becky Gillette, with her own money, she was a member of the Sierra Club, investigated this. And she found out that what she thought, and it was proved she was correct by the EPA, that formaldehyde in the air was making these people sick. They were being exposed to a high level of formaldehyde and very sick, and even their pets, some of them died. Well, she tested it with her own money, found a company, and then President Bush, the second one, and the head of FEMA, who was in charge of cleaning up, a guy named Brown. President Bush hired some guy with no experience. The only experience he had was running horse shows. You can look it up. It's disgusting, but true. Fought Becky. And they even tried to get the EPA to say, no, you're wrong. Well, they tested and they found out, no, she was right. And when I first heard about Becky in the news, I said, wait, I'm a world authority on formaldehyde. Let me track her down. I did. I called her. I said, Becky, I'm now being a consultant because I was no longer working for that company. I was teaching and consulting at this time, teaching at ECC and another school. And I said, any way I can help you, I will. I will never charge you a penny. And she did ask me to help her in things. And one of the things I learned about was, and I told her, it's probably the wood. And what do I mean by that? Well, because of the hurricane, people boarding up their houses and everything, there was a tremendous shortage of plywood and the wood they used to make the trailers. So what did those companies probably did? I can't prove it in a court of law because I don't have that kind of ability to track down what they bought, but they probably bought it from China. And it costs money to bring down the formaldehyde level in the resins glues to make plywood and particle board. And if you're in China, you have no OSHA. And why should I spend extra money? There was a lot of unreacted, we call that free formaldehyde, in the resin that was used to make the plywood and particle board. In the United States, that wouldn't happen because of OSHA. And the companies like I work for who made those resins for what we call forest products, plywood, had to keep the free formaldehyde very low so people didn't get sick from it. Well, tell you a quick story. Becky called me up and said, could you call this person up in Washington and educate them about formaldehyde and how it's coming out of wood? I said, sure. And turned out to be the lead investigator for the then select committee of the House of Representatives, who he was the chairman, Congressman Henry Waxman. And I told him everything I've just told you. As we talked, and afterward, at the end, we were talking on the phone for almost an hour. I said, I know coming up soon, this is why I was asked to talk to him. Henry Waxman, Congressman Waxman, is going to have a televised hearing about this problem. And he's going to have the owners of the trailers in front of the cameras, television cameras, in that hearing. And I asked this investigator, I forgot his name, could you ask the congressman to ask one question of these owners? And he said, what? I said, ask them where they buy their wood. And immediately like that, he said, I can't. And immediately I knew he knew what the problem was, but what they were doing was this show, we call it an industry dog and pony show. Oh, look, we're doing something about this. They're trying. No, they weren't. And years later, there was a situation where a company called Lumber Liquidators that make flooring, wood flooring, bought their stuff from China, and the Chinese companies were saying, oh, it's low, and it wasn't. That's why it was so cheap. And CBS 60 Minutes did a great documentary on that. One other thing Becky asked me to do, at that time, California, which for many years has been leading the country toward better environmental laws, came up with what's called the CARB law, California Air and Resource Board law, that limited the amount of free formaldehyde in wood products. And Becky asked me, can you write a letter, because of your credentials, to the administrator of the EPA, the head of the EPA, to try and support getting those CARB laws enforced throughout the whole United States, not just California. And she asked me then, President Bush was no longer president. It was President Obama, and I wrote to him. And I'm sure I'm not the only one who wrote. And luckily, a year or two later, or maybe less, those have been enacted in the United States. I did get a nice form letter back from President Obama. You could tell it was auto-signed, but it was nice. I still have it in my file cabinet as a memento. Now, what that means is if you have cabinets made, and this is, I found out from a woman who worked with Becky also, new cabinets that are not solid wood, and they were made in China. A number of years ago, they probably did. Now they don't, maybe or maybe not. You should have that room tested for formaldehyde. If you know anybody, or if you have a newborn, first one, well, I'm going to go out and get all this new furniture for my baby's room. Well, if it's not solid wood, it's probably made in China, and that could also have a formaldehyde problem. And what I'd like to show you now this is Becky's website. I haven't talked to her. Hold on, what did I do wrong? Huh, hold on. I don't know why I can't find it. Huh, maybe she finally took it down. But anyways, there's a company that tests them. I'll look it up. I can't find it right now. Let's do something else, maybe because I put a space in there. Nope, maybe she finally took it down. But anyways, there's a company I can look up that you can find that tests for formaldehyde. You email them or contact them. They'll send you a little kit and you have a choice. Do you want the results back by US mail or email? And it's about $40. And they send you a disc. You put it in a room you want to test overnight, seal it, mail it back to them, and they'll analyze it. This was the company President Bush and head of FEMA tried to show you're wrong. And the EPA, when Bush brought them in to try and prove that company was wrong, said, nope, they're spot on. And I wanted to tell you that. And with that, this is a good time to take a break. Let's come back at 1:55 by my clock in about 6 minutes, and we'll continue on. I'm back. I was looking out my weather window, and the ground is not frozen on my back deck. But if you look at all the branches on the trees or the bushes in my backyard, they've got ice on them. It's coming down pretty quick now, too. All right, let's get back to work. Now, switches off. Where do you find aldehydes and ketones? Well, you learn benzaldehyde, cinnamaldehyde. I wonder what that's in. It's in vanilla. I mean, it's in cinnamon. I was looking at the next name. And it has a structure. And there's actually a trans double bond. That's this aldehyde. That's the common name right here. Vanillin, you should have looked up. And if you'd like the taste of raspberries, and I do, there's an aromatic ketone that is responsible for that taste. Switch is totally off on this slide. Now, how do you make aldehydes and ketones? Well, we just went through this in the alcohol problem set, so I'm not going to do it again. But if you take I'll give you one problem. If you take an alcohol, primary alcohol, oxidize it, you'll get an aldehyde. So primary alcohol, oxidized aldehyde. And I really shouldn't cheat you out of some practice time, so I won't. And here's one for you to do. Give the organic product or products for the following reaction. And I see the votes are coming in. Please be patient and try and give everybody time to finish. And remember, tonight I'll have my office hours. So if you have any questions, it's on Zoom, so come on by. All right, let me do this now. Look for what's different, what's not carbon or hydrogen. Oh, oxygen with a hydrogen on a carbon, and carbon's here, and you're oxidizing it. That's what O, bracket O, close bracket. And this is a primary alcohol. I'll never ask you to name what kind of alcohol, but I'll use the terminology. And when you oxidize it, there's hydrogen here and here, and you form an aldehyde. What's R? This. Another way of thinking it is got 1, 2, 3, 4 carbons across. I better end up with 4 carbons. And on this carbon right here, I have 2 methyl groups. Now, this carbon here is this carbon, which becomes this carbon, which is this carbon, double bond to oxygen with a hydrogen. And I know there are 4 bonds to carbon. And there's your structure. Now, if you take a secondary alcohol, 2 R groups on the carbon with the hydroxyl group, this one, R and R prime. And remember, R and R prime is just like in math, X and Y numbers. Here it's carbon hydrogens, however many, and you oxidize it, you make a ketone. So it's time to try another one. And the question is 3 points each. Give the organic product or products are the following. All right, everybody's done. My turn. If we look at the starting material, what's different, what's not carbon, what's not hydrogen? Ooh, oxygen with a hydrogen on this carbon, but there are carbons here and here. That's a secondary alcohol. Doesn't have to be in a ring, but I thought I'd put one in because Dr. White loves rings. And when you oxidize it, you lose this hydrogen and this one and form a carbonyl, carbon double bond to oxygen. Now my R and R prime is the ring plus this and propyl group. Do you break carbon-carbon single bonds? No. So I'm going to get it back. It's going to come along for the ride. Now this carbon is this carbon right there, which is this one. So that means I have my carbonyl to the ring, and that's my product. And here's one more. As I mentioned earlier, on test 2, I'll have 3 or 4 synthesis problems. So the synthesis problem would be give the starting material or starting materials for the following reaction to make that product. And I'll be nice if it's more than one. So I usually don't put a question mark if it's just one, but if it's more than one, I'll put more than one question mark. But since you're practicing now here, I'll put a question mark. And this is the fun part of organic chemistry. Well, I'm biased. I'm a synthetic organic chemist. Remember, synthesis is a fancy word meaning to make. And thank you all for registering your vote. And please be patient. I try and give everybody time to finish. All right, let's do this. How do you do this? How do you figure out what do you oxidize? And that's what O in a bracket, closed bracket means to make this product. You look for what's different, what's not carbon, hydrogen, and an oxygen, double bond to carbon with a hydrogen on this carbon. And I have these carbons I'll call R. And this is an aldehyde. And what do I oxidize? That's what this means. I start with a primary alcohol. And what's our two carbons? Then this carbon right here becomes this carbon, which I'll now add. And it's an alcohol. And I know there are 4 bonds to carbon. And that's how you do synthesis. And remember, on test 2, all the general reactions except for the ones with, I'll tell you, which so far has been with ethylene oxide reactions. I won't do those for synthesis, but anything else is fair game, unless I said it's not. All right, let's move on. Now, the gentleman chemist you learned before, Friedel and Crafts, who did alkylation, also came up with Friedel Crafts acylation. I'll never ask on a test, but this is called an acyl group. How they got that name, I have no idea, but it is. And what you do is react a benzene ring. This is called an acid chloride. And unfortunately, we don't have enough time to talk about acid chlorides, but they're very useful and reactive. And this is a carbon right there. And you use aluminum trichloride, and on the benzene ring, you replace one of the hydrogens with this acyl group from the acid chloride. You also make HCl, but that's an organic. So we look at the following. And the question is, what's the organic product or product? What's different? Ooh, a benzene ring. Don't forget to put the double bonds or circle in there. Then carbon, carbonyl, chlorine to the carbonyl. This is an acid chloride. Ooh, and we also have aluminum trichloride as a catalyst. And you have your benzene ring, carbonyl, and R group. I forgot to mention, this is an aromatic ketone. And what's our methyl? So I'm going to have my benzene ring, carbonyl, carbon, double bond, oxygen. What's my R group? Methyl. And I've now made that compound. It's got a common name called acetophenone, which I'll never ask on a test. And that's Friedel Crafts acylation. It allows you to make what we call aromatic ketones. In a little while, I'll say, why is that important? Your turn. Give the organic product or products to the following. When you see me looking over there, I'm looking at the poll to make sure everybody's finished. If we're in a classroom, I could just look around and say, everybody finished? And the answer is, I think, just about. Let me give a little more time. All right, let's do this. What do we have that's different? Ooh, a benzene ring. That's different. What do we have here? Carbon, carbon, carbonyl with the chlorine, an acid chloride. And we have a catalyst, aluminum trichloride. And what you get is this aromatic ketone. Don't forget to put the lines in a ring or circle, carbonyl, and my R group. What's my R group? 2 carbons. So I have my carbonyl, my benzene ring, carbonyl, and 2 carbons. And there are 3 bonds to carbon. So there's the structure. Now, as I said, there'll be a couple of synthesis problems. Let's have you try one. And the question would be, first of all, let me fix up this hydrogen. Looks awful. That's better. What two things would you react with aluminum trichloride to make this compound? Your turn. Like I said, this is the fun part. And the votes are coming in. Remember, if you have any problems with anything, always feel free to ask, either now or in my office hour. All right, let's take a look at this. We look at the product. What's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Ooh, I've got a benzene ring. I've got this oxygen double bonded to carbon bonded to the benzene ring. And I have these carbons I'll call R. I have an aromatic ketone. I have aluminum chloride. And now what do I react to get that product? Benzene plus an acid chloride. So one of the question marks is a benzene ring. And the other, what's R? Isopropyl, carbonyl, chloride, chlorine atom to that. And there are 4 bonds to carbon, so I'm going to put in the hydrogens. Now, there's something special about aromatic compounds, ketones. They absorb UV radiation. And the question is, why are you learning these reactions? Well, the obvious answer is you want to get a good grade in this class because somebody told you you needed it to get into a program or school. But if we look at the following reaction, what do we have that's different? A benzene ring, an acid chloride, where R is a benzene ring here, and aluminum trichloride. And you make this aromatic ketone. Now, R is a benzene ring too, so you get this compound. And this is called benzophenone. I won't ask on a test, but why are you learning this? Well, for many, many years, this is the active ingredient in sunscreens and suntan lotion to protect your skin from the dangerous UV radiation of the sun. I won't go into the chemistry, which I could. How does it absorb that? But it does. Now, a number of years ago, they found this was the tiniest possible carcinogen. And in European Union, they outlawed it, benzophenone. They found if they put a methyl group on one of these rings, some are, it's not as little dangerous. And that's what's being used now. Now, another thing, aromatic ketones are used to make what are called radical activators. And there's a branch of chemistry, which I'm not going to go into, and I really haven't worked in it, but I know about it, called photochemistry. And when that absorbs certain type of energy, light, it forms a radical that can make other things react real quick. And where do you find that? Well, if you have your nail polish you put under the light, there's an aromatic ketone absorbing that energy, transferring it to make polymers, and I'll teach you about that later on. That's how it hardens it. Now, in the printing industry, if you're at a newspaper, which I guess with the internet, their sales have gone down, but if you need high-speed printing, you put the ink with a aromatic ketone in there on the paper, then have it go under a UV light, and that cures the ink, so it's no longer wet. And that's the beauty of aromatic ketones. Now, it's called photochemistry. And if I had to, I could do a whole 2-semester course, graduate level, on photochemistry. It's one of the few areas of organic chemistry I have worked in an industry. All right, let's move on. Let's go back and talk about the carbonyl group. Now, what I'm going to tell you on this in the next 1 or 2 slides, click, the switch will be off. It won't be on a test or the final. Now, oxygen, remember carbonyl, oxygen, double bond to oxygen. And if R prime is hydrogen, it's an aldehyde. If R prime is carbons, it's a ketone. Now, if you look at the periodic table, as you go to the right, atoms or elements are more electronegative, and oxygen is to the right of carbon. What does that mean? The pi bond, remember any double bond, 1 pi bond, 1 sigma bond. The electrons, electronegativity means if we're sharing electrons, I'm going to share them a little closer to me because I'm bigger and stronger than you are. What that means is you get this. Well, my lights just flash. I hope I don't lose power. If I do, well, come back next week. But this right here is smaller case. Delta, the Greek letter. This is uppercase or capitalized delta, the Greek letter. This means difference. If you've had other chemistry, you'll see like delta T, change in temperature, and things like that. When you use the smaller case, that means, are you ready for this? Little difference. Isn't that cute? Now, you know I'm an organic chemist. And again, this won't be on a test ever. So this means there's a small or slight negative charge on the oxygen, and there's a small positive charge on the carbonyl carbon. And because of that, nucleophilic attack occurs at the carbonyl carbon of the carbonyl group. What's that nucleophilic attack? Well, phile means lover. Nucleus, that's the center of an atom. That's always positive charge. And this is something that's looking for a positive charge. And if I'm a nucleophile, this gets my attention big time. I want that. So switch still off. Let me just do one thing. Anyways, when you have a nucleophilic attack, it attacks the carbonyl carbon. If Nu minus the nucleophile, it attacks that. The electrons from the pi bond go to the oxygen. That's one way of doing it. And then you could also think of it this way. If you had a nucleophile that's H plus Nu minus, and I'm not going to put anything on the board. But anyways, the nucleophile will attack the carbonyl carbon, and the hydrogen H plus will go to the oxygen, and you break the pi bond. All right, can I have everybody's attention? Everybody take a deep breath. Let it out. Take a deep breath. Let it out. Let's do it one more time. Take a deep breath. Notice I close my eyes, get nice and comfortable. Let it out. The next 4 reactions I'll talk about are some of the reactions, probably the foremost of this semester, that gives students trouble. Relax. With a little practice, you'll get it. But at first, what's going on here? So let's get to that. The first one is called formation of hemiacetal, hemiketal. Now, this should be a carbon here. My software doesn't like to put it in. Same thing here. Now, let me rewrite this to help you out. If R prime is a hydrogen, that's an aldehyde. If R prime is carbons, then it would be ketone. So what I'm writing here is take an aldehyde or ketone, react it with an alcohol, ROH. Now we're getting to some good stuff. And you need an acid catalyst. This is an acid catalyst. Keep your eye on the carbonyl carbon, because that's where the fun is. What's attached to that, R prime or hydrogen, and R double prime stays there. But this right here, you get an OH, and the oxygen R group from the alcohol bond to this. And this one is start with an aldehyde, I'll never ask on a test, is called a hemiacetal. When it starts with a ketone, it's a hemiketal. And one of the questions you can ask is, why are we learning this hard stuff? Well, later in the semester, you'll learn this is a reaction Mother Nature used the first step to make carbohydrates and another reaction. I don't know about you, but if you like potatoes, rice, or French fries, or potato chips, this is the next reaction Mother Nature uses to make the starches, the carbohydrates that make those items. So let's take this first spin. And if we look at this reaction, and by the way, this is just a long slash, what's the product or products of this reaction? Well, we have to look what's different. The first one, we've got a carbonyl with a hydrogen and our group here, but this also could have been R prime, aldehyde or ketone. Then if we look here, carbons with a hydroxyl group, this is an alcohol, acid catalyst. Keep your eye on the carbonyl. What's attached to it stays attached to it. R prime or hydrogen plus R double prime. And this attacks that H plus RO and opens it up to this hydroxyl group on that same carbon, OR, which comes from here. So if we look here, I call this R double prime, R prime, and this is R. So I'm going to start with this carbon, which came from this carbon, this carbon. What was attached to it? R prime is a hydrogen. R double prime methyl. We look here, we have OH, then oxygen. What's my R group? Ethyl. And this is the molecule. I'm not going to ask you to learn how to name it. I can, but we're not. And this is a molecule that, not this one, but this reaction, Mother Nature uses. So let's have you try one. And the question is, what's the product or products of the following? Now, to ease your mind, hopefully it does, I will never give this reaction as a synthesis problem. I can do it, but students have a lot of trouble doing synthesis. But I will ask you, give the product or products of the following. No, we're getting some really good stuff. That's not what I wanted. Keep your eye on the carbonyl carbon, carbon double bond oxygen. That's where the fun is. I said, at first, these are very complex reactions, but with a little practice, you'll get them. And please be patient. I try and give everybody time to finish. And one of the things I should mention, if you want in private, if I'm not giving you enough time to finish your reaction, let me know by either email, stay after class, and we can talk in private, and I'll try and give you a little more time, or come to my office hour. All right, I think everybody's done. Let's do it. We look at both of these molecules. What's different? Ooh, what's not carbon? What's not hydrogen? Get your attention like that. I've got an oxygen bonded to carbon, double bonded carbonyl. I've got carbons here I'll call R prime, but it could have been hydrogen. It doesn't matter which you call R prime and R double prime. And here I have carbons here. I'll call that R double prime. In this case, we have a ketone. Oh, wait, look at this molecule, carbon hydroxy group with an acid catalyst. That's an alcohol. And keep your eye on the carbonyl. Carbon, what's attached to it, R prime or hydrogen, and R double prime are still there. This part opens up to an alcohol. It's not really an alcohol, hydroxyl group. And then from the alcohol part, you get oxygen R. And what's my R right there? So I'm going to keep my eye on the carbonyl carbon, draw that first. What's attached to it, R prime, and then R double prime. And then I'll have my hydroxyl group, because this is what my general reaction shows me. Then O, and what's my R group? Methyl. And that's how you do it. Oh, let's do one more. Now, I should mention the carbon with the hydroxyl group in the alcohol, this carbon is the same carbon in this R in the product that has the oxygen on it. All right, your turn. This one's a little trickier, but let's see if you're up to the challenge. Like I said, this is a little more sophisticated and challenging reaction, but with time, you'll get it. All right, I think everybody's done, so let's do it. Now, if we look at the first compound right here, what's there? Ooh, oxygen, double bond to carbon, carbonyl. It's got carbons here, here. This is a cyclic ketone. Here, our prime and our double prime are connected together. Could have been an aldehyde, it's not. And what do we have here? Ooh, hydroxyl group on a carbon. That's an alcohol plus acid catalyst. Let's clean that up. And what do you get? Keep your eye on the carbonyl. What's attached to that? Oops, I got ahead of myself. That happens once in a while. What's attached to this right here stays attached to it. Our prime or hydrogen, our double prime. Then this opens up the hydroxyl group O, R, and the R comes from the alcohol. So what's my R prime and R double prime? This whole ring. So it's still going to be attached to the carbon here that was the carbonyl, which is this carbon. This will have a hydroxyl group. Doesn't matter which side you put it on. Oxygen. And what's R? Right here, isopropyl. The carbon with the hydroxyl group is the carbon bonded to this oxygen, which is here. That's the center of 3. Oops, this one. Now, if you wanted to draw it this way, running out of room here. You could have, either one is correct on a test. And luckily, I have a piece of paper from the Board of Regents of Michigan State University signed that I know this, my PhD diploma in organic chemistry. If I look at that, oh, I went over a whole 2 minutes. Bad, Dr. White. All right, let's take a 5-minute break, come back at about 5 minutes from now, whatever your clock is saying, and we'll do our lab and we'll be done. With that, I'm going to take a break and stretch and look out my weather window, see what's going on out there, and I'll see you in about 5 minutes. Sorry about the delay. I was looking at my front and back weather window. Let's get started. It's raining pretty good out there, but the street I live in is it's got traffic on it, but not that much. I saw a couple cars zooming by, and that means it's not icy, but my branches in front and back, my backyard and my front lawn on the trees and bushes are ice coated. All right, let's get back to work. It's time for the lab. Give me a second while I close some things up. And next, open something. All right, today's lab. Does everybody see the lab on the screen? Give me a thumbs up if you see. Thank you. All right, this is called aromatic electrophilic substitution lab. Now, if we were doing it in the lab, you would be working with concentrated sulfuric and nitric acid. This is one of those labs when I do it face to face. Dr. White is at DEFCON 4 or 5. That means I'm looking at everybody to make sure they're doing things safely, because sulfuric acid concentrated and concentrated nitric are very dangerous. It eats your skin. We call that an acid burn. But in all the years I've been teaching it, I only had one person have a very slight little accident at ECC. At COD, I had one person had a bad accident and he didn't follow directions. Well, that only happened twice. But anyways, the reaction we're talking about is electrophilic substitution. We're taking a benzene ring, react with E as an electrophile, and replace one of the hydrogens. Remember, what we do in the lab never is on any test or the final. I'll say that again. What we do in the lab is never on a test or a final. Now, with this reaction, any electrophile like nitration, sulfonation, alkylation, doesn't matter which carbon you put the electrophile in. I'll show you in a second, we'll be doing nitration. But what if there's something on there, a group? And in organic chemistry, somebody came up with the idea for this situation, the group on there we'll just call Z, because it can be many different things. And if you have the electrophile, it can react to replace the hydrogen here and this one, and that's ortho position. 1, 2, or 1, 2. And I put it on here, and this is called an ortho director. Z would be an ortho director. Now, if Z is something different, it could direct the incoming E group to this, which is the meta position. It doesn't matter which side you put the E on. And that's a meta director. And finally, if Z is a para director, here's the para position, the electrophile goes there. Now, it turns out, and this is important, that in this lab, you'll be reacting bromobenzene with sulfuric and nitric acid to put a nitro group on a nitrating. And you'll determine, is bromine what type of director? Now, one of the things I want to point out, and pay attention, hint, Now, there are only two types of directors. One is called an ortho-pair director, also abbreviated OP director. And the reason we call them directors, have you ever gone to a concert where a county fair where they take this open big field or parking lot without any markings, and they have the people say, park there or go down there. No, don't park there. Fill this up first. They don't like me because I don't listen to them. I don't like them because I don't listen to them. They get mad at me. But anyways, the Z group is the same thing, telling the group coming in, our lab will be NO2 group nitro, where to go. And this is a meta director. Now, there's a certain aspect or part of organic chemistry called steric hindrance, crowding. If Z is very large, you probably aren't going to see in an ortho-pair director any ortho product. Because normally ortho-pair director gives you both ortho and para. But if Z is very large, big atom or big Z group, you won't get any ortho product, but this is still called pair director. It's not a pair director. You only have two choices for Z. It's either ortho pair director or meta director. So if Z is real large, you won't see any ortho, but you'll get the para, but it's still called an ortho pair director. And this lab, you're going to find out what is bromine. And you're going to start with bromobenzene and react it with nitric acid and sulfuric acid and find out what type of director this is. Now, I'm going to do something, don't get confused. I don't want to give away the answer. So I'm going to write it this way. What's the product? And I'm going to write it this way. And all that tells you is somewhere, either ortho, meta, or para, or ortho para, or meta, the nitro group will go on there. Now, an important part of the reaction, when you see the procedure, you start out with sulfuric acid, and think of sulfuric acid as H+. And you react it, add nitric acid. You do this cold slowly. And why do you do that first? Let's write nitric acid this way. Well, the lone non-bonding electrons attract the proton from the sulfuric acid. And you make this intermediate. But if you ever have a molecule or intermediate, and I'm putting it in brackets because you can't isolate it, notice right here, let's go with Technicolor. Anybody see something familiar in those, inside the circle, the red dots? Let's see. What? Two hydrogens and an oxygen. Two hydrogens and an oxygen. H2O, oh, it's water. And whenever you can, lose a very stable molecule. I can't think of anything more stable than water. You show that by minus H2O, minus meaning it's gone, H2O water. What do you have left? This. This is the nitronium ion. And therefore, this is the key reason why you react sulfuric acid as H plus with nitric acid, because you form the nitronium ion, and that's what attacks the benzene. It's got a plus charge. It's looking for electrons, and a benzene ring has electrons, and that's what happens. Oops, time out. And I apologize, but with all the things I've got going on this machine, what happens is I have a couple hundred files opened up, sub-files, and my machine says, oh, wait, I don't know if it goes, but you get the message. All right, let's get back to work. So if we were doing this lab, and I'd ask you, since we're not, look at the following YouTubes. I'm not going to show it to you. You can do it on your own time. Now, if we were in the lab, you take a round bottom flat or beaker water first and heat it up because you need to have boiling water. Now, if we were in the lab, I tell you in a beaker where you have a hot plate, we don't use Bunsen burners. Oh, by the way, when I do artwork, I better warn you, I'm not an artist, and don't laugh your head off too much or hurt yourself. But anyways, if you have a beaker in glass, when you boil water, you form bubbles. If you don't have what's called boiling chips or boiling stones, you got these massive bubbles and the water shoots up. I mean, it can shoot up real high. So I always tell students to do that. We put a clamp on here, clamp it to a ring stand, and I teach you that, and that keeps the beaker from falling off and hurting people. All right, we get that started first. Next, in a round bottom flask, you'd add 3 milliliters of a concentrated sulfuric acid solution using a funnel in the beaker, round bottom. That's even by my standards, a bad funnel. And that student who had the accident didn't use a funnel, was trying to get the eyedropper of the acid into a small hole. No, you use a funnel. Now, after you do that, you cool it in an ice bath, and we have what's called a recrystallization dish where you have ice and water. It's cold. It absorbs heat. And you stir it around for a while to get the sulfuric acid in here, cold. Next, very slowly, in different parts, you add 3 milliliters of the nitric acid through the funnel. And that's really the part the student had that accident at the other school. He didn't use a funnel, got nitric acid on his arm. And I asked, what happened? Oh, I got nervous and I twitched, and he twitched and squeezed the eyedropper and ended at his arm. Since then, I have students, when we do it face to face, you always wear a lab coat or a long sleeve top or shirt that protects your skin. We always wear gloves for this, and safety goggles always in a lab, even if it's just water. and you'll add it, swirl it for a couple minutes, take it out of the ice bath, let it cool for a couple minutes or warm up, and then in one aliquot, all at the same time, through the funnel, you'll add 1.6 milliliters of bromobenzene. Now, after it comes up to room temperature, give it a couple minutes, 5-10 minutes, you'll clamp it and put it into boiling water. Now, one of the things I haven't talked about in this class is in real life, you have what's known as side reactions, where other things can be formed. And this reaction, depending on the purity of the nitric and sulfuric acid, which isn't the super pure stuff, we don't buy that, you don't need to. All of a sudden, after a while, you'll see this brown smoke. Now, we're in a fume hood that traps anything coming out of there, pulls it up by a fan that pulls a slight vacuum, and sends it out the roof of the building we're in, and that gets diluted by the wind. Now, the nitrogen dioxide, that brown smoke, is a poison. And I tell students and warn them, because otherwise they get very scared. And you'll boil it for a while, 25 minutes, take it out, let it cool, and then you'll show me the salad. Unfortunately, in the face-to-face, we only have an hour, 50 minutes to do the slab where you isolate the actual salad. It would take about 2 hours and 20 minutes, 2 hours and 30 minutes, which how do I know that? Because we do that at COD, College of DuPage, where we have a 2 hour and 50-minute lab period for this. Now, what I do is come around, and when you have to show me your salad, it's nice yellow color, and I tell you what's the melting point. Now, for this lab, the products you could get are in this table, either ortho-bromonitrobenzene, meta-nitro-bromonitrobenzene, or para-nitrobenzene. Since it's a solid, you can take the melting point you learned in the first lab that helps identify. You need to write right here the ID of your product, what you just made. And that's based on the melting point here. Now, in real life, when you're doing this reaction, since you're not really purifying it, and also you're new to melting points compared to how many I've done, your melting point is always going to be a little below what the actual melting point of that product is. It'll never be way above. So based on that melting point, you can identify the product. Now, here's some questions. And if you're paying attention, you should be able to answer that. And that's today's lab. And with that, I'm done for today. And I will remind you, if you have any questions, come to my office hour from 6 to 7:15 tonight. If you need special help, email me and I'll see if I can set up a private Zoom meeting when we're both available. And I do that since we've been on Zoom for students who say you're working tonight or whatever. Also, don't forget, on Monday, I will go through the ether and epoxide problem set. I highly recommend you do it on your own first. We're speeding up, and then I do that face-to-face. We're covering more, and you have to keep up. Well, you don't have to, but if you want to do good, and I hope you do, keep up with the problem sets. With that, I'm done. So I'll say, remember in Yiddish, it means gehen gesund, go in hell. Gehen gesund, go in hell, gehen gesund. I stole that from Granny to Beverly Hillbillies. Bye now. Have a great rest of the weekend.